All right, hello everybody. So let's get back here to the computer. Then I will show you some more slides. We will recap everything and then wrap up for today. So again, don't forget that we have exam number 3 on Friday, okay? And you will have 24 hours to return the exam to me. You can submit it through Canvas, so that's easier. Then I can just download it at once. Okay. All right. So let's do the share screen process, and I will share my PowerPoint with you. Okay, here we are. Awesome. So that was the point we stopped last week. So I showed you that the octahedral complex can undergo an associative mechanism and produce a coordination number 7 complex, or dissociative produce a coordination number 5. And each of these configurations, they have different energies for the orbitals because the repulsion between ligand and the orbitals will be different. And using the ligand field stabilization energy, we can have an idea about if the complex is inert or labile. Okay, so we did that for D1, D2, and D3. So we found out that D1 and D2 are labile and D3 is inert. And we also did, right, some minutes ago for D4 low and high spin. So I have here a summary for all the high spin configurations. And as a conclusion, we will say that D1, D2, D7, D9, D10, high spin D4, D5, and D6 form labile metal complexes, okay? And same thing for low spin. So all the D6, D7, D5, and D4 low spin metal complexes, they form inert complexes. In addition, D3 and D8. Okay, I don't know if these graphs will help you or not, but here what I tried to do was to plot ligand field stabilization energy for OH, C4V, and D5H configurations as a function of the number of d electrons. So first one is, of course, 1, 2, 3, 4, all the way to 10. Okay, so the black dot is the energy of the octahedral configuration, and the red and blue dots are the energy of the C4V and D5H configurations respectively. So you can see here that for D1, the C4V and D5H configurations have a higher ligand field stabilization energy. Same thing for D2. However, when we move to D3, then the octahedral configuration will have higher ligand field stabilization energy than the other two possibilities. Therefore, D3 is inert. Okay, so this here is for high spin complexes, and the one on your right side is for low spin complexes. And here again, a summary of the deconfigurations that form labile complexes and the deconfigurations that form inert metal complexes. So if you recall some months ago when we synthesized some cobalt complexes, we always started from cobalt 2 plus and not cobalt 3 plus. So why that? So if you have a periodic table with you, open it. Cobalt belongs to the group 9. Therefore, cobalt 2 plus will be D7, while cobalt 3 plus will be D6. As you can see here, D7 configuration is labile, while D6 may be labile or inert. In most of the cases, the cobalt complex are low spin in that case, therefore will be less reactive than cobalt 2 plus. So that's why we always start with cobalt 2 plus, because it will always form labile metal complexes and then at the end oxidize to cobalt 3 plus, sorry, and then you will form an inert metal complex. Okay. And that's the reason that people, when they started studying metal complexes, the cobalt 3 plus was the favorite because usually is very stable in solution. Okay, so I showed you 4 factors that influence the substitution in organic reactions: size of the metal, oxidation state, chelate effect, and the energy of the intermediate that we calculated together using the ligand field stabilization energy. And remember, if the energy of any of the 2 intermediates possible is higher than the ligand field stabilization energy of the octahedral complex, the metal complex will be labile. Okay, so let's move on. So today I would like just to introduce this new topic, and we will cover it in more details on Wednesday. Okay, so now let's talk a little bit about the substitution in square planar complexes. So we have here the example of 2 platinum 2 plus complexes. So platinum 2 plus is a D8 metal complex, and D8 configurations usually form square planar complexes, especially the heavy atoms from the group 10, which are palladium and platinum. They usually form square planar complexes. All right, so let's start with tetrachloroplatinato or platinate 2. If we add a huge excess of ammonia, we will observe only the formation of the cis product, only the cis product is formed. However, if we start from the tetra amino platinum 2 and add excess of chloride, only the trans product is formed. Our question is why? Why, if we started with only chloro ligands, we only form the cis, and why starting with only amino ligands, we only form the trans? Okay, so that's what we will study on Wednesday. And I think this is a good point to stop, and I will see you back on Wednesday, okay? I hope you have a good day. If you have any questions, just let me know.